Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
If you are there and I am here, we can measure the distance between us. And if we are standing in a room, we can calculate the area of where we're standing. And if we want, the volume of the room itself. These are all examples of measures, which essentially tell us how much stuff we have or how big something is. So what is a measure? How are distance, area, and volume related? And how big is a Sierpinski triangle? All of this and more on this episode of Breaking Math. Episode 57? You said how much? I'm Sophia, and you're listening to Breaking Math. With me, we have on Meryl Flaherty. Meryl, thank you for being on the show.
Thank you.
And you work at the University of New Mexico, correct?
That's right. I am a PhD student and a teaching assistant.
And today we're going to be talking about measure theory. But first, we're going to do a couple of plugs. First of all, if you want a poster, which is an introduction to tensors, you can go to facebook.com/breakingmathpodcast. The poster is there for $15.15, which is e to the e dollars, plus $4.50 shipping and handling, coming to a total of $19.65. It also has a little introduction to Einstein's general theory of relativity, or at least how you use tensors with it. If you want to support us monthly, you can do so on Patreon. For $1 or more, we have a tier where we deliver outlines. And if you donate $22.46 or more, we will give you the same poster that you could buy on Facebook. But that's just a support thing because obviously it's more expensive there. You can also find updates about the show there. We're on Twitter at BreakingMathPod. Our website is breakingmathpodcast.app. And you can email us at breakingmathpodcast@gmail.com with ideas, comments, questions, and corrections. And if you want to, you can listen to our sister podcast, Turning Rabbit Holes, which Gabriel's on. All right, so we're talking about measure theory, right? So what is measure theory?
So pretty much measure theory describes the size of things. So like if you have some set or some shape or whatever, how big is it and in what dimension?
All right, so if we're talking about length, obviously, right? You calculate the distance using, you measure along the length, correct?
That's right, and there's one dimension. And right, so length is just one dimension, so it's what your measure is in that one dimension.
Yeah, so the measure of a path in 2 dimensions would be 0, right?
Right, so the circumference of a circle would be a one-dimensional measure because a circle itself is what we call a one-dimensional manifold.
Yeah, definitely. And if we took the circle instead, though, as the points within a 2D space, we would have to be measuring the area, right, if we use the 2D measure, right?
Right, and so...
And in that case, it would be different.
Yeah, so it's like, say we take the circumference of a circle, so that's a one-dimensional measure, but let's say that we take the area within that circle, now that's a two-dimensional measure.
Yeah, and a 3-dimensional measure is like the volume that a sphere occupies. A 4-dimensional measure might be like, I don't know, like some kind of hypervolume. It's pretty intuitive. I mean, and also one thing that we notice with measures is that if I have a sphere, right, and I fill it up with a bunch of cubes, all those cubes will add together to equal the sphere, right?
Right, provided that you keep making the cubes smaller and you keep giving us more and more cubes.
Yeah, so that's what we mean by the measure of something. It is how much stuff exists within something. And there's measures that exist for things that aren't just strictly Euclidean sets. There's like measures for fractal dimensions as well. And we're going to talk about those as well. All right, so length, area, volume, those are all part of something called Lebesgue measure, right?
Yeah, and that's kind of a generalization of measure, or more specifically, a generalization of integrals.
Yeah, because we're going to talk about later how we can have fractional dimensions, like the dimension of a Sierpinski triangle, which is that triangle where you keep cutting out the middle triangle over and over again, kind of like a fractal version of the Zelda icon. The Triforce. Yeah, but whole number dimensions in a Euclidean space have a measure that can be characterized all by Lebesgue measure. So first of all, we're going to talk about Lebesgue measure in one dimension. So first of all, we're going to talk about what it means to have a subset of the real numbers. So a subset of the real numbers might be 0 to 3, right?
Yeah.
But I don't know. Do you want to give a more colorful example of a set within the real numbers?
So there's all sorts of ways you could go with this. You could do something like negative infinity to 0, non-inclusive, and that's all of the negative reals. Or you could do something like negative 3 to negative 2, unioned with, let's say, like 0 to 1. And so those are two just disjoint sets that are joined together.
Yeah, and you could even have like infinitely detailed sets, correct? Like if we took the length from 0 to 1 and took out the middle third over and over again. I forget
so,
the Hilbert thing.
The Cantor set is
Cantor
that?
set, yeah. Not Hilbert set. But
nothing.
But yeah, so all of these are subsets of the real line, right?
Ultimately they are.
And to measure them, what we have to do is we have to define the Lebesgue measure. So the Lebesgue measure is defined, we're going to just do the mathematical definition real quick. It's defined as the infimum, which is the minimum, basically, like the minimum of all possible things within a certain definition. And that definition is that we're using here is the sum of lengths of some set of intervals that cover what we're talking about. And covering just means that these lengths all together, like all the union of all of them. Well, let's talk about the union real quick. It's going to be important. So what is the union between the closed interval from 0 to 1 and the closed interval from 1 to 2?
So in this case, union means something different than what workers do to collectively bargain. In this case, it means that we're joining two sets together, basically. Is that it's like you have a set, what were the numbers you said?
0 to 1 and 1 to 2.
Okay. So let's say that you have one interval from 0 to 1, and you have another interval from 1 to 2. And is this inclusive or non-inclusive?
Inclusive.
Okay, so let's say it is inclusive. So 0 and 1 are members of that 0 to 1 interval, and 1 and 2 are members of this 1 to 2 interval. And so we would write that with square brackets for those intervals. Then, so the union of these then would be, it should just be the closed or square bracket interval from 0 to 2.
Yeah, because the interval from 0 to 1 contains every number greater than 0, less than 1, and 0 and 1. And the union of the interval from 0 to 1 and the interval from 3 to 4 is just, it would just be all the numbers between 0 and 1 and 3 and 4, right?
Yeah, so those numbers between 1 and 3 then, those are not part of the set. Yeah, so if we have the union between 0 and 1 and 3 and 4, then all those numbers between 1 and 3 are not part of the set.
Yeah, so like 2.5 or something like that would not be part of the set, but like 1/2 would be, because 1/2 is greater than 0 and less than 1.
Exactly.
And so, and yeah, and we can't really simplify that any further than that. We just have to say the union between the interval from 0 to 1 and from 3 to 4. To get maybe a clearer picture of this, we could use a physical example. So suppose there's some road that's infinitely long, but a lot of it has weeds, right? So we're going to say that this road is the set of all real numbers. And let's say we go like, I don't know, like a foot down the road. We're at the number 1, 2 feet is 2, and so forth, right?
Right.
And we're going to say that if there's a weed, which could be infinitely tiny, next to some section of road, then that section of road is within some set, or the number it represents, and so forth. Is that clear?
Yeah, so what I'm getting is that this is a setup for sort of like the Dirichlet function.
I mean, it could be for the Dirichlet function if we had like these infinitely tiny weeds. The Dirichlet function is 1 where there's irrational numbers and 0 where there's rational numbers. And you can do the integral of it, but I'm talking about more like just a setup. Like, so if we're talking about the set between -1 and 3, to the left of the point that was a 0, 1 foot down that road, they're covered with weeds all the way to 3 feet in the other direction, right?
Okay, so weeds at this point are being used as an analogy for intervals.
Yeah, and like patches of weeds, etc. Exactly. Yeah, where an interval is like, from 0 to whatever and so forth. So let's say there's 2 people with giant backpacks full of pesticides that start at the 0 point and walk down the road in opposite directions. So they could spray haphazardly, right? Like they could spray back and forth. So we're going to say that that one spray of this pesticide is enough to kill a weed. So the optimal spray in a pesticide will not spray the same weed twice, right?
That sounds right.
And we don't want to spray patches of road that don't have weeds on them, because we'll still be wasting a pesticide. So let's say that we have some spray pattern that uses the minimal amount of pesticide, right? That is kind of like the Lebesgue measure of the weeds. Or you can even talk about it as the time that the sprayer is on. Because remember, they're walking down the road at a constant rate. So if the sprayer is on for like 3 seconds, and they've walked for however distance, it'll be a 1-to-1 correspondence, right?
Yeah. And just so I'm clear on this, what we're looking at is we want the least amount of pesticide possible that will kill all the weeds.
Yeah, exactly. Yeah, minimum amount of pesticide or minimum time that the pesticide thing was on for.
Okay. That makes a lot more sense, actually.
Yeah, and so you can look at the spray of the pesticide as the sets that are part of the covering set, right? Because when the pesticide is turned on, if you take that time and subtract it from when it's turned off, and you add all those up, it'll be the total time that it's been on for. And also, if you take the pesticide, the amount that remains, if you take that from the amount that you started with, and you add all those up, you get the amount that you've used in total, right?
Right.
So that's an analogy that you can maybe use to understand this a little better. And so let's say we have, so that's one dimension, right?
Assuming that the road itself is one-dimensional, sure.
Yeah, we're mathematicians. Roads are one-dimensional and cows are spherical.
in a frictionless perfect vacuum.
It sucks too, because I tried to go to the store the other day and I couldn't walk there.
Just kept slipping.
Now I wasn't even tumbling because my muscles couldn't. None of this works. But anyway, yes, it's Math World. So let's say 2 dimensions, right? You could visualize this, the covering set of, like, let's say a circle as a bunch of squares that cover it. So, like, let's say you're in Microsoft Paint or some kind of drawing program like that, and you keep drawing squares. If you draw blue squares over, like, a picture of something red, like a skull or a circle, and if you cover it so there's no red remaining, then that could be considered a covering in 2 dimensions. The infimum of those is the Lebesgue measure. And in 3 dimensions, it would obviously be cubes, right?
Right. And so what I'm getting at here is that, so let's assume that all of these cubes are equally sized, and cubes, squares, whatever, are equally sized, and we're using them to cover whatever shape, whatever set we're looking at. Then we get a clearer idea of the size of this thing if we keep making the cubes or squares or whatever smaller, and we keep counting how many of those there are.
Yeah, because we can start off with some big cubes, right, that like block off a lot of the area, but then just kind of make them smaller and smaller and smaller, and fill up more and more of the area. Yeah, so maybe the big squares fill up 95% of it, or the smaller ones fill up 99%, and so on, all the way up to 100 theoretically. As long as we're in an integer number of dimensions, right? We're pretty good so far. But let's say we have a fractal. So, do you want to talk about what it means to have a non-integer number of dimensions?
So, before I do that, I do think I need to explain something about dimensions. So, a good way to describe dimensions is that, so let's say that you have just a square, and you multiply all of its side lengths by some constant, let's say r. Then its area, as you scale something by r, is going to scale by r squared. Or with the cube, you scale the side length, and the volume will then scale by r cubed.
And that works with any shape, right? If I have 2 dragons that are copies of one another, dragon statues, and the length between one dragon's eyes and its tail is twice what another is, it'll have 8 times the volume, right?
Right, because 8 is 2 cubed. So the thing about that, though, is let's say that we have a fractal shape, and it can be anything, a Sierpinski triangle, the Cantor set.
And the Sierpinski triangle, just again, is you take a solid triangle, you take out the middle third from that triangle, the middle, like a triangle facing downward. So you have 3 upwards facing triangles. From each of those, you do the same thing to what you did to the first triangle. So now you have 9 little triangles. You do it again, so you have 27 and so forth.
Yeah.
And the Cantor set is where you keep removing the middle third of a line between 0 and 1.
And then you remove the middle thirds of those remaining intervals. And you keep doing that on and on until you have a set that is infinitely many points. But
what's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit 1 million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
0 length.
Yeah, so, I mean, it is kind of the one-dimensional version of the Sierpinski triangle now that I think about it.
Something like that. So here's the thing, though, is that going back to the Sierpinski triangle, so what happens as you keep cutting out more triangles from this is that you get something where, and you can use the series for the area or for the perimeter to calculate this, that it would have 0 area yet infinite perimeter.
Yeah, and the reason why is, we could do it super quick. I mean, you take out 1/3 of something over and over again, it's going to go to zero, right? Because there's no lower part. There's nothing that it converges to, right?
Right. It just goes to zero.
Yeah, I mean, I guess it's a quarter of the area, but yeah, you take out a quarter every time and it keeps going to zero. Because it's 3/4 to the infinitieth power, which is, just go on a calculator, keep multiplying it by 3/4, and it'll go as low as you want.
And right, so what we have is a sequence of we have some real number to the power of n, and so what we get is that this number is less than 1, so the more we raise n, we see that it eventually goes to 0.
But the perimeter is the opposite way, because one of the small triangles has half of the perimeter of the big triangle, because it's a triangle half the size, so each side is half as big, so basically it's half of the total length. But there's 3 of them, so we have to multiply by 3 halves each time, adding 50% over and over again.
And doing the same thing, raising that power until we go to infinity, we see that that perimeter itself also goes to infinity.
So yeah, continue with what you were saying about the difficulty of measuring this.
Right. So the way that mathematicians have gone about this is that, so we can't define the size of this in length, and we can't define the size of this in area, and clearly it doesn't have volume. So we decide instead, what if we try to find something in between this where we can measure its volume, or content, or measure, I suppose is the correct word for it here.
So before we go on to that, I should give the formula, or a formula for finding the dimension of certain things. So if I multiply, so the Sierpinski triangle is 3 copies of itself. If you double it, right?
Yeah.
But a square doubling it is 4 copies, right?
Sounds right so far.
And a cube doubling it is 8 copies.
Yeah, so powers of 2.
Yeah, and that's dimension 3 and dimension 2 for those two. And it turns out if you take the log of 8 divided by the log of 2, it's 3, because log base 2 of 8 is 3. Another identity, we'll do that some other time. And log 4 divided by log 2 is 2. So it turns out that we could do log 3 because we tripled the Sierpinski triangle, right? Divided by log 2 because it's double the size. And arrive at the dimension equal to log 3 divided by log 2, which is 1.58496, etc. But Meryl, tell us more about it.
Okay, so Minkowski-Bulagon dimension, also known as box counting dimension, is a specific way of estimating a fractal or fractional dimension, which go hand in hand in this case. The way that it goes is that you count a number of boxes that cover a shape that you're looking at, and
so let's say we're talking about the coastline of Indonesia.
So let's say that we have boxes of some certain length, and we'll call it what people usually use is epsilon.
Like some very small number? I've seen delta for those as far as boxes go lately.
Huh. Well, doesn't matter. We're just assigning letters to things. So what happens is, let's say that you have a bunch of boxes of length epsilon, and you can cover the coastline of Indonesia with these. So there's a certain number of boxes of length epsilon that you need to cover that. And
so epsilon, it's a number that gets smaller, right? It's like a limit, right?
Yeah.
So let's say we start off with epsilon being 1 foot. What would that look like if we were to physically do this to Indonesia?
So I might not start at 1 foot, but let's say let's go for something really big.
20 miles?
Yeah, let's go crazy. Let's go 100 miles. So it's like you're just going to get these big chunks of coastline, and it's not really going to give you an accurate description of the length of the coastline.
And it's a minimal covering, right? Because we could theoretically put boxes all over the coastline, like hundreds of thousands of these big coastline boxes, but we're talking about the minimum number that fit within.
Yeah, so just don't let your boxes intersect. Just try to get the smallest number of boxes possible that are 100-mile side length to cover this coast. Now, what we want to do is we want to start making them smaller, and we'll get a more accurate representation, right?
Oh yeah, absolutely. I mean, I suppose what you're getting at is like if we made them like a mile big, then we'd start getting like coves and individual islands.
Right. And so as we keep making these boxes smaller, we keep getting more and more details. And what we see
Like
is
individual coves and coast and grains of sand, right?
right.
So this progression of boxes as they get smaller, right? Each covering, so we have a covering for 100-mile big boxes, a covering of 1-mile big boxes, and as we get to micron and nanometer boxes, these are all to calculate a dimension, right? A number instead of a collection of things, right? We just need one simple number from it.
Okay. So a really rough description of how we get dimension out of this is how many more boxes. So how does the number of boxes scale with the refinement of the size of the boxes? So as the boxes get smaller, how many more boxes do we need to cover this coastline?
Yeah, so the Minkowski-Bulligan dimension of the coastline of England is approximated to about 1.25, for example, which means it's a little bit more one-dimensional than the Sierpinski triangle.
Right, so it's a little too complex to just use length to calculate.
Yeah, which is fascinating. And Mandelbrot decided to publish a paper called "What is the Coastline of Great Britain?"
How
right?
long is the coastline of Great Britain?
And everybody was like, "What the heck are you talking about? Like, just look it up in an atlas." And then didn't he publish another one? He's like, "No, really, how much is it?"
And I guess to go back to the analogy, it's like, sure, let's say that you take a yardstick and you just keep measuring and adding up till you've gone all around Great Britain. Then it's like, you'll get some value. But let's say that you just get a foot-long ruler now, and you don't know. Let's get stupid with it. Let's just make it an inch-long ruler.
And so on.
And you'll notice that this length that you get will keep increasing and increasing. The smaller of this ruler you get, it'll eventually, let's say that, someone out there, for some incomprehensible reason, had a millimeter-long ruler. You would get a value that is way greater than you did with your foot-long ruler.
That in turn would be greater than the meter-long ruler.
Yeah, it would eventually go to infinity because you have something that is self-similar and infinitely complex, and the length would go to infinity.
Yeah, or, I mean, very, very high. There would be a finite number of particles, and if we measured their electromagnetic boundaries, there must be some smooth function.
Okay, we'll use applied mathematics terms. We'll just say it gets arbitrarily large.
So one way to measure the amount of stuff that's within something that works for fractals is, so the Hausdorff measure, so let's say we have a covering, right, of this thing that we're taking the Hausdorff measure of. And we're adding up. So let's just imagine that these are balls in whatever dimension that we have, right? So if we're doing the Sierpinski triangle, the balls would be embedded within 2 dimensions, right?
Yeah, even though that they would be log 2 of 3-dimensional balls, but
yeah,
that's a little counterintuitive.
Yeah, and that is the power you would raise it to. So basically, like, we're imagining that these are like little like cubes or little balls or little whatever. It doesn't really matter. So that they cover this set that we're measuring. As the balls get smaller and smaller, all we have to do is take their diameter and raise it to the power of s, where the diameter gets smaller than some number delta, and we'll get what's called the Hausdorff measure. So it's the infimum of the sum of the diameters of the individual sets of some set of sets that covers a set that we're measuring, and each of these is raised to the power of some number s. But if s gets too big, then the Hausdorff dimension is 0, right?
Right, and I think I have an easier way to visualize this.
Please.
Yeah. So let's say that we have a square, then we know that it has an area, that it has a dimension of 2, right?
Yeah.
But let's say that we try to take a volume of this square, then, well, we haven't extruded it out into 3 dimensions, so it's just going to be 0.
Yeah.
And it doesn't matter whatever the dimension is, if it's larger than 2, that measure is going to be 0. And same thing for, like, if you have a cube, then if you try to take some sort of 4-dimensional measure, or it doesn't matter, let's say we have a 3.3-dimensional measure, it's still going to be 0 because it's greater than 3.
Yeah, and in the same way, a line that is one-dimensional, that is infinitely thin, will have no measure in 2 or 3 dimensions.
Yeah,
or
so
more.
it would have no area, no volume, no 4-dimensional measure.
But yeah, so this is the Hausdorff measure. So let's take a simple fractal, right? The Sierpinski triangle. Meryl, you're an educated grad student. You should know the Hausdorff measure of the Sierpinski triangle.
If I'm not mistaken, it's log 2 of 3.
Well, that's a Hausdorff dimension. But the Hausdorff measure, this is weird about the Sierpinski triangle because Hausdorff dimension is known, right? And the Hausdorff dimension comes from the Hausdorff measure. But we only know that through properties of the Hausdorff dimension. Basically, the Hausdorff measure is a surprisingly current problem. It's something that it has a bound between 0.77 and 0.8191612328811177. Or there's a paper, which is in a paper by Peter Moore, but there's another paper by Heiyu Wang and Xinghua Wang, which gives another estimate that's a little bit closer. But the point is it's an unsolved problem. And it turns out that the reason why it's still unsolved, so a level 1 Sierpinski triangle is just a triangle, right?
I think that would be the 0 iterations, actually.
Oh, yeah, that's right. Yeah, 0 iteration.
Yeah,
it's just a triangle, right?
Yeah, the first iteration is you cut a triangle out of the middle. So, you get your typical Legend of Zelda Triforce.
Yeah, and then you cut it again, you get a Triforce made of Triforces. Cut it at level 3 is a Triforce made out of Triforces, made out of Triforces, and so forth. So it turns out that counting the number of Triforces within a specific disk or like radius is not a solved problem. And it's kind of easy to know that it's not solved because, I mean, just think about the regular grid, right? Like if I get an infinite graph paper, the number of points within a circle that I draw is not going to be something that we can that we know currently. So yeah, this is known as a Gauss circle problem, which basically states that the amount of points, it's a question that is still unsolved as to how quickly the amount of points within a circle of some radius r grows. And the points within a Sierpinski triangle are distributed a lot more complicatedly than that. And so the fact that it's not known is pretty expected. A level 30 Sierpinski triangle has 159,310,733,867,010 triangles that need to be considered while doing a simulation. And I know that when Peter was doing their simulation, it took like 4 days at this resolution, and it triples each time, which shows the difficulty in finding these numbers, and also the fact that lower bounds and upper bounds currently have to be estimated by slightly different means. The paper by Heiyu Wang and Xinghua Wang, we're trying to get more information on that. Currently, it's only in Chinese, but I'm trying to get some help with that, and hopefully we'll have an update with you on that. I just found it kind of interesting that it's so hard to measure this, you know?
Yeah, but it also makes sense because it is a very complicated sequence that we're looking at.
Yeah, just the regularity makes it seem like it should be much easier to figure out stuff about. But yeah, I guess it is counting those things. It's just one of those weird, like, sometimes you turn a corner in mathematics and you just hit a wall, you know?
Yeah, and that's the thing. It's like infinitely complex things like this can just come out of the simplest of rules. And making a Sierpinski triangle is about the simplest rule you could come up with. You're just cutting triangles out of triangles.
Yeah, and it doesn't help that we've just started in the last 150 years to study this. Like, there's really, like, mathematics takes quite a long time.
Yeah, for us mathematicians, 150 years is like 5 seconds.
Yeah, but we chip away, we chip away continuously at this gigantic sculpture. The amount of stuff within something is the task that gets harder the more complex of shapes we look at. But this just means the measure theory is a fertile ground for further development. I'm Sophia, and this has been Breaking Math. With us we had on today Meryl Flaherty, who is a grad student at the University of New Mexico and teaches there. Any impressions about the show today? Any further thoughts?
There's just a lot on this subject, and I could talk to you about it for days, especially because fractals in particular and fractal geometry are a special personal favorite of mine, and I could just gush about it if I wanted to.
All right. Was that a little lame? It was a little lame. I don't care.
We're doing math. Of course, we're lame.